We are now dealing with the terms involved or related to convex lens and concave lens. We have seen what is optic center, then we have seen what is center of curvature. Two center of curvatures are there, C1 and C2, and also done radius of curvature. Now here we will be seeing the next term, principal foci. Foci is the plural, focus is the singular form. So we actually got two surfaces which are capable of refracting. So when you deal with one convex lens, it will be having two principal foci. Two focus 1 and focus 2 will be there, and in case of concave lens also, two focus 1 and focus 2 will be there on either side of the lenses. So that is why we call principal foci. So here first we'll see the first principal focal point of convex lens. So I have shown a convex lens here, and optic center is marked, and there is a reference line going through the point O in the vertical manner. So that is the reference line, or we consider that the refraction is happening at that point. Okay, because we are taking a thin lens, so the thickness of the lens is not considered here, and we simply assume that the refraction is happening at this reference point rather than at these two surfaces. It is just for simplifying the ray diagram. So in the first case, what you are going to deal is to define the first focal point. So it can be seen that when rays are coming from a certain point from left to right, so this is left and this is right. This is the section of first surface, and this is the section of second surface. So when a ray of light is passing from left to right in a convex lens, it can be seen that when the ray is coming from a particular point, those rays will, after refraction, will go parallel to the principal axis. So principal axis is this one. So it is seen that if the ray is coming from a particular point on the principal axis, can be seen that those rays, after refraction through the convex lens, it goes parallel. So such a point is known as first focal point of what? Convex lens. Okay, so first focal point of the convex lens can be defined as a point on the principal focus, the ray from which after refraction will go parallel to the principal axis, and we represent that first focal point as F1. Okay, capital F1. And there is a distance between this first focal point and the optic center O, that is OF1. We name that to be the focal length, first focal length of convex lens. The distance between optic center and the first focal point is known as first focal length, this length. Okay, and if you consider a plane means a two-dimensional plane like this, which is passing through the first principal focal point, that plane is known as first principal focal plane. Okay, suppose you consider that there is a plane or a surface which is passing through, imaginary surface which is passing through the first principal point, so that will be inside the board like this. Okay, so that plane or surface is known as first principal focal plane of convex lens. Okay, so I'll define it once more. The first focal point of convex lens is the point on the principal axis, the ray from which after refraction will go parallel to the principal axis. The distance between the first focal point and optic center is known as first focal length, and the plane passing through the first focal point is known as first focal plane. Okay, same way we can define the principal focal point for concave lens also. Okay, so in concave lens, how we define is, suppose the ray, we know that in convex lens it is a kind of convergence, whereas in the case of concave lens it is a kind of divergence. Okay, so the way in which we define the focal point for concave, first focal point for the concave lens is, suppose rays are coming, it is actually it seems to be coming, that is, here it is f1. So here this is ray, first ray, this is second ray. So it seems to be coming from, or coming point towards the focal point. Okay, the ray is moving towards the focal point or single point on the principal axis. Okay, and after that is when it strikes these ray, when it strikes the concave lens, it is seen that it is refracted and it goes parallel to the principal axis. Okay, so the ray from which the incident ray is imagined to emerge from, or is imagined to meet at a point which is known as f1, and that point we name that to be first focal point of concave lens. So for concave lens, when you are defining, we can define it in this way. The first focal point, it is a point on the principal axis such that the incident ray, these are the incident rays, such that the incident ray will appear to meet at that particular point. Okay, after refraction from the lens will become parallel to the principal axis. So it seems to be a little bit confusing, but the only fact is, the ray which is coming and striking the concave lens, if the ray is going parallel to the principal axis, then you can say that the ray which appear to come or appear to meet at a particular point, that point is known as first focal point. Okay, so that is about the first focal point of concave lens. Now if you analyze the first focal point of concave and convex lens, they are on two sides. Here the first f1 is on left side, whereas for the concave case it is on the right side. So in center of curvature also you saw that for convex and concave, the sides are actually C1 and C2 were in the opposite sides. Similarly, the first focal point is also on the opposite sides. Here convex case it is on left side, and concave case it is on the right side. Similar to the other case, here also we have focal length. Focal length is always the length between the first focal point and the optic center. And here also there will be a focal plane which is passing through the first focal point of the lens. So that is about the first focal point of convex and concave lens. Okay, now we'll see the second focal point of convex and concave lens. It is I think it is a little bit more easier to understand, better than the first focal point. Now we'll see that. So next we will see the second focal point of convex lens and concave lens. Actually the first focal point and second focal point, it can be interchange, because we won't specifically hold the lens only in one position. It can be in either ways, but when you are defining, in mirrors also we have learned about sign conventions and all. So that according to that sign convention only we are taking all these definitions. Okay, so according to sign convention, you know that the ray will always come from left to right. So we learn according to that convention. Okay, so it doesn't mean that we should hold the lens only in one particular position. It can be interchanged also. Okay, now let us define the second focal point. So the second focal point means, for convex lens, suppose parallel rays are coming and striking the convex lens, that is parallel ray parallel to principal axis are striking the convex lens. As I told, we will take the refraction from the reference line. Okay, so it is striking the lens and is refracted. you could see that all the parallel rays which are parallel to principal axis, after refraction they will meet at a single point, and that single point we name to be second focal point. Okay, first focal point, what we did is the rays were coming from the focus and were going parallel after refraction, whereas second focal point is defined how? The rays parallel to principal axis after refraction through a convex lens will converge or will meet at a single point F2, which is known as second focal point, and the distance between the second focal point F2 and O, the optic center, we name that to be second focal length, and the plane which is passing through the F2 or second focal point, we name that to be second focal plane. Okay, so that is the definition of second focal point. It is easy to learn compared to the first focal point. Now in the case of concave lens also, the same thing is happening here. That is, we have parallel rays. I have taken two parallel rays which are parallel to principal axis. After refraction through a concave lens, you know concave lens is diverging lens. They will diverge. Okay, these two rays will diverge, and they appears to diverge from, that is, if you are back tracing, they appears to diverge from a single point which is known as second focal point of concave lens. So when you are defining the focal points, it should be defined specifically for concave lens and for convex lens separately. Okay, so second focal point of concave lens can be defined in this way: if parallel rays parallel to the principal axis after striking the concave lens refract, and if the refracting ray appears to diverge from a single point, that single point is known as second focal point of concave lens, and the distance between F2 and O, or second focal point, and the optic center, we name that to be focal length, second focal length, and the plane second focal plane. Okay, so that is about the definition of principal focal length and principal focal points of convex and concave lens. Okay, and when you are drawing, as I told earlier also, you should show the arrow marks. All the rays, incident ray as well as the refracted ray, everywhere the arrow marks should be drawn. The back tracing should be shown using dotted lines. The principal axis can be drawn using solid line, whereas this reference line, okay, that you can consider or taken as dotted line. Okay, now next we will see more details of this, how the images are formed and all, using this convex and concave cases. Now you know that there can be parallel rays which are not parallel to principal axis. So in the previous case we have seen parallel rays which are parallel to principal axis, and after refraction through convex lens they will converge to a single point which is known as focal point. Now there are cases in which the parallel rays can be oblique. Oblique means slanting position with principal axis. So in such cases, of course, since it is a converging lens, they all will converge to a single point, but that single point won't be the focal point. Okay, so it will be a point which lies on the focal plane but not on the principal axis. Okay, so it will be somewhere else on the focal plane. So anyway, any principal or any parallel ray, whether it is oblique or parallel to principal axis, they will converge and they will meet at any point on the focal plane. It can be any point. Only the parallel ray parallel to principal axis will converge to which point? The focal point. Okay, so these points, other points which are on the focal plane, we don't call it as focal point. Okay, so the diagram is shown here. So many oblique rays are there parallel to each other. After refraction, you could see that all the rays will merge or will converge to a particular point. And when you are drawing, these converging points should be on the focal plane, not on the focus. It should be on the focal plane at any other place. Okay, so that is about the oblique ray convergence. Similarly, for this case, where concave case also the same thing will happen. You could see that here it will be the focus 2, and this is the point B. So here also I have considered certain oblique rays. So this oblique ray will diverge, the second oblique ray will go straight because it is passing through optic center. The third oblique ray is also diverging, and if you trace back all the divergent ray, you see that all of them will meet at a single point, but that single point is not on the focus F2. That will be on the plane, focal plane, but not on the principal axis. Okay, so that is about the oblique ray refraction. Got it? For both the cases, that is for convex lens and concave lens, if oblique ray is coming and striking the lens and the refraction is happening, either the converging point or the diverging point from where the ray appear to spread will be at a single point, but that single point won't be on the focal point, but it will be on the focal plane, anywhere on the plane depending upon the angle of inclination. Okay, it depends upon the angle of inclination. Now when you speak of focal point or focus of a concave lens or convex lens, we mainly mention it as the second focus focal point. Okay, so suppose if we are simply saying the focus of a convex lens is so and so much, we mean that it is the second focal point or second focus. We found the different foci of a lens, first focal point, second focal point of convex lens and concave lens, and also found what is focal plane, how the light behaves when it is parallel to the principal axis and when it is falling obliquely. Parallel rays are falling obliquely on the lens. Okay, now so and we named the focal length. Focal point is represented using capital F, and so we have two focal points, F1 and F2, and the focal length, it is represented using the small letters. Okay, small F1 and F1 and F2, small F1 and F2. And in this both the cases, that is convex lens and concave lens, we have seen that this F1 and F2 are on both sides of the convex lens and concave lens. But when you see the value of focal length F1 and F2 for biconvex or double convex lens, you could see that numerically this F1 will be equal to F2. Okay, numerically the value of F1 and F2 are same. Since the surface or the curvature of both are same, they have same focal length, whether it is in convex lens or concave lens. Numerically they are both same. Now when you take the case of convex lens, we say that the convex lens have real focal length. Okay, the focal length of convex lens is or focus of convex lens is considered to be real. So convex lens got real focus. So the reason is, after refraction through a convex lens, the rays actually meet at a point. So that is why we say the focus of convex lens is real. Whereas in the case of concave lens, it is having the focus is said to be virtual. Okay, so focus is virtual for concave lens. The reason is, as you know, for concave lens the divergence is happening, and the divergent ray or the refracted ray will appear to come from a particular point. It is not actually coming from, it appears to come from a particular point. That is why we say that the focus of concave lens is virtual in nature. So those are the main points to be kept in mind. The focal length f1 and f2 are numerically equal. Convex lens focus is said to be real. Concave lens focus is said to be virtual. Again, when you move to the numerical portions and all, we'll see that the focus of or focal length of convex lens is taken as positive and focal length of concave lens is taken as negative and all. That we'll do later. Now the last section of this convex lens and concave lens, this unit is the difference between convex lens and concave lens. Before that, let me say one more thing, that is the focal length of convex lens or concave lens depends upon only two factors. The first factor is the refractive index. Okay, refractive index of the material of the prism. That if it is glass, you know the refractive index will be near to 1.5. The second factor in which the focal length depends is the radii of curvature, R. Radii of curvature. You know, two radius of curvature are there, so we name that to be radii of curvature. Okay, so these two factors are only affecting the focal length, the refractive index of the prism and the radii of curvature. Now we'll see the difference between convex lens and concave lens. First one, the convex lens. Convex lens, when we did the definition, we found that it is thick in the middle and it is thin at the periphery. You know, it is thick at the middle and it is thin at the periphery. Whereas concave lens, the lens thickness will be more at the periphery than at the middle region. Middle region will be thin. Now the second thing is, it converges the ray. That is, convex lens converges the ray. That means all the rays after refraction will be converging or meeting at a single point. Whereas the concave lens, it diverges or it spreads and it appears to meet from a particular point. So it diverges the incident ray from the principal axis. Now the last one which we just mentioned, the convex lens got real focus, whereas the concave lens got virtual focus. So these are the three differences between convex lens and concave lens. Now in next unit we will be seeing how we can construct the ray diagrams for different situations.